Thrilled to be with everyone here today. Beautiful country, the Netherlands, beautiful day. Been wonderful hosts. First of all, a little bit more about the clicker's broken now. There we go. A little bit more about me. So I was originally on the founding team at Pinecone. Before that, I was a founder. My background was in Python and C++, doing sort of machine learning, PyTorch, etc. And then I got involved in the database space and grew the org at Pinecone to over 50 engineers using Rust all up and down the stack. We have probably hundreds of thousands of lines of code, something like 40, 50 PRs a day going in to our monorepo. And so we're huge fans of Rust, and I want to share a little bit more about why Rust is such a uniquely good fit for the use case of building a vector database. There we go. So first of all, what is a vector embedding? A lot of people, I don't think, are familiar with this. A vector embedding is just a high-dimensional matrix, essentially, that represents a point in Euclidean space, right? And so these are important because an embedding means that it's imbued with meaning, right? If you have two words that are similar, say Friday, Thursday, whatever, days of the week, they're going to be represented close to each other in Euclidean space. Similarly, you can do sort of like operations with these because they're imbued with meaning. If you subtract them or etc., these geometries actually represent real things. So what is a vector database? A vector database is a database specifically tailored to storing these representations and searching them, generally with approximated algorithms in high dimensions, very low latencies. The things you might store in a vector database are images, right? You can put them through a convolutional neural network, and then you get a vector embedding representation, and you can find all the similar images, right? So this is people use it for text, people use it for images, they use it for product search, right? You can embed movies, products in a catalog, anything, and build recommender systems and search systems. So what's required to build a vector database that can actually support this application? We need complex data structures, right? We're often having graphs or different types of in-memory indexes. We need efficient algorithms, and we need distributed operations to be able to swap data, update it asynchronously, and bring it to the right nodes for execution time. I'm just going to switch to this. So we started with Python and C++ as our stack. It seemed like a reasonable choice at the time. We had our high-performance algorithms written in C++, and then the code that was wrapping around them in Python. But ultimately, it didn't give us strict memory management, fast and stable performance, or efficient multi-threading. Because when you have, and those of you who've used Python, I'm sure know this, when you have, a memory leak, or any sort of performance issue, it's almost impossible to track down where it is between the garbage collector and all sorts of the other, weird aspects of the Python interpreter. So what do existing search engines use, right? We looked out there and we said, okay, there's similar products out there. You have Lucene, which is designed for traditional full text search, right? Used by Elasticsearch, Solr, OpenSearch, and so forth. And then you have traditional SQL or document databases that provide, search features, full text search, or different sorts of indexing algorithms, like MongoDB, Postgres, and these are generally written in C++, whereas like Lucene took sort of a Java approach. Right? But we wanted to try a more modern programming language. So let's rewrite all the code, right? Everyone loves when you rewrite the code. We decided to look at a few different languages. We looked at Go, we looked at Java, as I mentioned, and we looked at just, keeping the whole thing in C++, as well as Rust. Ultimately, spoiler alert, of course, we chose Rust. It's the best language clearly here for our use case. It has good performance management, good performance, good memory management. It's easy and lightweight integrations into local native instructions like SIMD, which is why you're all here. And it has very strong dependency management, of course, with Cargo. Some things weren't great with it. Obviously, it's a bit of a newer language compared to the others. So, you can't just Stack Overflow every single thing necessarily. But the overall third-party integrations are growing a lot. The community is clearly very strong. And so we took a bet on it. So now I'll get a little bit more into the details of what my team does, the algorithms team at Pinecone, and why we use some of the cutting edge features in Rust to build these high performance indexes. So first of all, let's talk a little bit about the difference between a dense and a sparse index. When you think of a traditional search engine, right, doing full text matching, you're thinking of a sparse index. A sparse index, you have the Rust, right? You look up those keywords, you find all the documents. We use inverted indexes, postings list for those of you that are familiar with this, and then we retrieve them. A dense index means that instead of, in this paradigm, right, the vast majority of the values in a given vector are 0, right? If you represent the document as a matrix, as a vector of like bits, let's say 1 hot, 1 0 0 0, you set the and Rust to 1 and 1, and then everything else in the vector is 0 up to the size of the English vocabulary, right? Because those are all the terms. And then you can do basically, an XOR or a dot product to calculate a score. Okay, how many documents are in the same? It's essentially a set intersection, right? Dense indexes, on the other hand, for more pattern matching, fuzzy, modern search methodology like semantic search are represented in Euclidean space. So here you don't have any exact pattern matching. You don't have a set intersection that you're doing. What you're actually performing is a Euclidean distance or a cosine distance lookup into high dimensional space. Obviously we visualize it in 3 dimensions here, but really you have thousands potentially of dimensions, and you want to build an index to find the nearest points in that space. So, okay, we've built these indexes. Now, how do we optimize index scans? Because it doesn't really matter if you have the slowest search database, right? No one's going to use you. These are often recommender systems. They're in the hot path for people. You go to check out, you see, or you go to Netflix and you see recommended movies, right? These are things that need to be low latency. So there's a few techniques for this. There's algorithmic techniques, which I'll cover briefly, such as early termination, compression, pruning, and then there's systems approaches, which again, this is why we love Rust. It allows us to get nitty gritty down in the details to actually make our code run as fast as possible. First, I'll cover some of these approaches for sparse indexes. So early termination is a methodology whereby we basically find a bounding condition. I don't know if any of you are familiar with this algorithm, but essentially, as I talked about earlier, we have this concept of posting lists where you look up some words like the Rust, and then you try to find the relevant documents. Max score is an algorithm by which we know that we can iterate over the term lists in a certain order. Have an upper bound that basically says, okay, if there's the highest scoring term in this document, plus all the other highest scoring terms in the postings list ranked lower than that, wouldn't put this document into the top K heap, then we can just exit, right? We no longer need to consider new documents from this postings list, okay? So this is the kind of technique that we would use to improve an index scan, and you can see here, once we actually reach this terminating condition, we just start ignoring the posting list, and we still calculate the scores for the other lists, but in this specific list, we don't care anymore. No document from this list that only exists in this list is going to be sufficiently high scoring to make it into our top candidate set. How much does this help us? Quite a bit, right? So this is almost a 5 to 10x improvement over just like a naive scan on inverted index indexes. And so like, okay, great. You know, we've made a fast search index. How do we make it even faster? So here's where we start to get really into why we love Rust, right? CargoFlame Graph. Phenomenal tool, right? Super easy to use out of the box. The profiler, I can just, you know, make sure all of my code is factored in such a way that it has, it's in functions and I can tell what's going on. And then I can just get a profile and you can see based on this about 50% of the time, a little bit more time is spent iterating the non-essential lists or the essential lists, which is what we would expect. Those are the lists that we need to do an exhaustive search over. And then when we dive in a little bit, we see that a lot of time is spent sort of in iterating, and there's no obvious bottlenecks here. It would be great if there were more granularity here, but a lot of this, I think, is just sort of pointer manipulation and stuff that isn't being captured. How do we make it even faster? Okay, enable release mode. Sorry, guys, that's it. I'm done. I'm going to go home. But SIMD is not a good fit here. It's frankly, because of the nature of the algorithm, you need to do sort of iterative lookups. And so there's no easy gains from using that. Okay, so now I'll move a little bit, and obviously, even though the talk is about SIMD, right, I also wanted to start with this just to showcase that it's not always a fit for optimizing algorithms. It's not a silver bullet, of course. And so, you know, going in now to dense ANN algorithms, this is here where we start to get a little bit more leverage out of using vectorized instructions like SIMD, because we're dealing with arithmetic over a large amount of numbers, calculating these distances in Euclidean space. Okay, so I'll talk first about a sort of naive technique for doing this using compression, right? So the idea is simple, right? We want to scan less data, okay? Think about an exhaustive search of a vector database, right? You have a bunch of floats. Let's say there are 1,000 dimensions. You have, you know, they're F32s. And so you have, you know, 4 bytes times 1,000. You have 4 kilobytes per document to scan, and you're going to be scanning, you know, maybe millions of them. So this easily becomes terabytes of data, right? You do not want to scan all of that and do an exhaustive search at runtime. So what's an easy way to fix that? We can compress it, right? Okay, how do we compress it? There's a technique called FJLT, Fast-Johnson-Lindenstra, I don't know how to pronounce that transform. And this takes d-dimensional vectors down to m bits. And so essentially, the way we do this, and I'm not going to get into the details, but you take a plane and sort of bisect the geometry and set a bit, either a 1 or a 0, based on a random sort of projection. And this preserves distances nearly between points, so it is an approximate algorithm. Obviously, it's a lossy compression, but then when you compute the Hamming distance, sort of this XOR intersection between the points at query time, you can reconstruct the approximate distances, either cosine or Euclidean in high dimensional geometry. So at query execution, as I mentioned, first we start with the full candidate set, and so this is where we scan the entire, you know, 100 million points or whatever is stored in the database. But as I said before, this is an approximation, and so it's not going to necessarily get us the correct results. So we do a cascading retrieval where we filter it down to a smaller candidate set. This candidate set is re-ranked with a higher fidelity metric. It might be 1 byte instead of 1 bit per dimension. And then in the final representation, we have 4 bytes, like an F32 for every dimension. And in most cases, we don't even need to calculate at that level of granularity, but we can do a final re-ranking with that as well, which will get us the true distances and the true ordering. That being said, of course, you may lose candidates at earlier stages. So this is the optimization. We want to choose algorithms that allow us to maximize the recall, right? The recall would be the number of candidates in the ground truth, which is the actual results that are, you know, within the closest distance to a given point, versus the results that you get based on the approximated scan. So how can we spin this up even more, right? Now we've figured out how to scan, you know, way less data, right? In many cases, 16 times less data. or more. And so but we can look to SIMD now to do that even better, because this operation clearly can be parallelized. These are, arithmetic operations that are happening sequentially. What are the tools? What are the toolkits that are available to do this? So there's AVX2, which has been around for a little while, since 2013. This is an extension to the x86 architecture, and the Rust compiler supports it automatically for a lot of cases, right? So if you're doing like U64 arithmetic, this will actually sort of happen. And then there's AVX512, which is a newer set of extensions to the x86 architecture, and this supports the 512 wide registers. And the interesting thing about AVX 512, or the not so interesting, the nasty thing about it, is that there's a lot of different features within it that are supported by different chips. So if you're looking at Ice Lake, Cascade Lake, every microarchitecture, you might have a certain subset of these AVX 512 features, but not others, which is also why we love Rust. It sort of allows us to manage this complexity. And huge shout out to the Rust team. I don't know if anyone is here who worked on this, but having Rust support for AVX 512 has been awesome. The final thing here is AMX, which is forward-looking. This isn't yet supported by Rust. This is introduced in 2020 by Intel, and this is a new instruction set specifically tailored towards sort of the new neural network paradigm and matrix operations, so sort of designed to supplant a little bit the CUDA workloads. It would be great to have Rust support for this. It's very hard to do right now. All right, so let's do a little bit of interactivity. This is some code. This is a naive function to calculate the Hamming distance like we talked about before. Does anyone in the audience have an idea about how we could change this to leverage SIMD? Yeah.
Maybe use a buffered reader?
A buffered reader. Interesting. I haven't. Yeah.
Ensure the length is like a multiple of sim lane width.
Yes, basically. Ding, 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 ding. So we need to align to 256 bits for AVX2. And so that allows us to automatically optimize the XOR pop count calculation. And we need to, in order to do that, we just convert the U8 slices into U64 before doing the XOR, and that gives us a magic 6x speed up. This is phenomenal, huge, easy win. And another thing that's nice about Rust, to be able to have a compiler that automatically does this. Cool. So, all right, coming back a little bit into the algorithmic side of things, how can we make dense scans even faster, right? We've already come up with a way to scan far less data using compressed representations, but what if we didn't even have to scan all the data at all, right? What if we could only scan a subset of the data? So this is where the approach called IVF comes in. IVF stands for inverted file lists. The idea is simple. We use sort of a k-means clustering to divide our high-dimensional vector space into partitions. Each partition has a centroid, which is the center of the partition. And then we map all the points in the index into one of those partitions based on which centroid it's closest to. At runtime, we can choose how many partitions to scan to allow us to do a sort of recall performance trade-off, right? So if we scan all the partitions, of course, we're going to have 100% recall. But if we can scan fewer partitions and sacrifice a little bit of accuracy for higher performance. Within each partition, we use another compression approach that's more advanced than the one I talked about previously. This is called product quantization, and it works very well with this in order to actually speed up and minimize the amount of data stored within each partition. So it's a hierarchical indexing scheme. Commonly, we scan around square root of n, where n is the size of the data partitions in this paradigm. I'll talk a little bit about product quantization. So product quantization is similar to the compression technique I discussed before, but it requires lookups into we call it code books. And so this technique essentially decomposes a high dimensional vector into a bunch of subvectors. It does a k-means clustering within the partition itself. And then it pre-computes essentially for each centroid, it has a score, and then it computes the residual to all of the points within that subpartition. And then at query time, you do a lookup whereby you get the code words, you look them up in the code book, and then you compute the score, adjust it to each point in that partition, which is a sort of a small integer. And then you reconstruct the score by computing it with the centroid in that partition, and then ultimately you get out back an approximate score. In practice, you can think about it like a smarter version of the compression algorithm I described before, because now we're decomposing the space and we're doing sort of like a custom compression rather than a random projection for every single point. At query time, as I discussed, we sort of take the subvectors, we compute the centroids across all the subvectors for a given partition, and then we get we aggregate the scores across all the subvectors to compute the total approximate score for a given query against a given document. Okay, so this is a great algorithm. It's well known, state of the art. But now we're saying, how do we make it even faster again, right? And we know that SIMD worked for the previous algorithm, right? Even though we didn't have to use any intrinsics, we used AVX2, it was good enough. But now we're saying, how can we reach state of the art? And so there's a paper on it. We referenced this, and essentially we chose to have 8 bits for the code words. That means we'll have 256 centroids. So each point has, 8 bits with it, which means it can point to one of 256 different centroids, right? And then we store the vectors in batches of 64. This allows us to basically align exactly into 512-bit registers and do the algorithm almost entirely with intrinsics to avoid all memory lookups and keep everything basically out, in the registers when possible and not in the L1 cache. So which intrinsics do we use, right? The first one is the gather operation. So this is ideally, we don't want to use it because this actually goes to memory. This goes to the L1 cache, but this allows us to quickly and deterministically populate the registers with, data from memory. And the second intrinsic that is actually much, much faster, so this is about 7 times faster when you don't have to go to memory at all, is just a permutation swap between two a pair of 512 wide registers. And so to the extent that you can do and write these algorithms just by operating across 2 registers with permutations, that's where you get the real gains in performance here. So how do we use these? So basically, this is an example of how we actually compute the distance, right? It only takes us 2 cycles to do the lookup because we use this, we basically break the code books into 4 chunks. We do 2 at a time, each is 256, and then we blend these with the blend intrinsic together and mask them to actually figure out basically which code books were which was the valid lookup. And so I'm not going to get too into the weeds of this algorithm. It's actually quite nasty, but essentially this shows you how you can really sort of factor any sort of algorithm to work with these intrinsics and get a big boost. The thing to note with product quantization that it's different, and the reason that we rely so heavily on these gather intrinsics is because it's very bottlenecked on the actual lookups. So whereas the first algorithm was just arithmetic, you just calculate against the compressed sort of flat vectors. Here you have to go do lookup into centroids for every single point, get some representation, combine that with the local representation, and then compute the distance to the query vector. Another way that we use Intrinsics for this algorithm is to actually load into memory and reshuffle data. So in certain cases, in the happy case, right, all the data is just sitting next to each other in memory or on disk or whatever, and it's very localized. But in practice, because Pinecone supports like filtering and deleting stuff, right, you end up with sparsity in these indexes sometime where data is fragmented across the space. And so in this case, you want to load it and rebuild the representation that you can scan. And we actually also use SIMD for this because it allows us to just pull in all the data at once, do some manipulation to produce the representations we want, and then put it into a byte array. So how much does this help us? 3x. Compared to a naive product quantization implementation in Rust. This is a phenomenal gain, right? This means that we're basically at state of the art compared to any dense ANN retrieval platform, and it allows us to scan maybe hundreds of millions of vectors, especially in conjunction with IVF that allows us to subset that in the order of 40, 50 milliseconds. Cool. And I talked a little bit about this before. Right. This is great. This is awesome. It's 3 times faster, but like, is it maintainable? Like, come on, right? Like, we're using all of these niche, intrinsics, these operating specific things that might work on Ice Lake but break on Cascade Lake and all of this stuff. But thanks to Rust, it's simple, right? You just have features, which features are enabled. They're automatically enabled for given targets. We actually do most of our development on Mac. So we don't even use these locally, just in production, and it's totally seamlessly handled for us. I have just a few more minutes. I'll talk about some of the other things we love about Rust. Zerocopy data formats. So this is another thing, of course, as a distributed database, we have data in blob storage, we have data in disk, then we load it in memory and do the scans. We don't want to pay the cost of serialization and deserialization. Zerocopy is super easy in Rust. I don't know if you all have heard of Archive. We use this a little bit. But we also just use raw bytes in and out because, it's an easy way to represent data. Monorepo. So as I touched on earlier, we have an engineering team of over 50 people in the same repo. We have unit tests, everything running with dependency matrices, targeting different builds. For every single pull request, we might build like 50 or 60 Docker images. I think we spend some amount that I'm not going to say here on CI/CD, but it's a very robust system, and Rust allows us to be really scale. It means everyone on the team can contribute to everything else, which is nice. Some struggles with Rust. This AVX512 is still unstable, which means, of course, we need to be on unstable to use it, which is not great. There's an open issue. I don't know if anyone here is involved or knows anyone who can help us do this. We'd be happy to contribute and help get this onto stable, as well as the support for AMX. Another few things with Rust, of course, there's always different ways to do things. This is the case with all programming languages, but we're debating internally all the time, interior mutability, different paradigms. But ultimately, Rust is safe, which is the most important thing, unless you do unsafe. And then another thing that I think would love to see more of in Rust, and I'm not sure, I just tried this like a year or two ago, so I don't know if anything is new, but benchmarking for memory utilization wasn't super easy out of the box. I would love for Cargo Bench to support, or the ecosystem to support some tools for getting memory utilization. We basically used a hack whereby we get the memory from the system and then report it to Criterion. Cool. Thanks so much for the talk. Stay in touch with me and follow me on Twitter. And we're hiring. If you're interested in working on some of the stuff that I've talked about here, algorithms in Rust, reach out to me. Thank you.
Are there any questions? If you have questions, please, would be helpful if you try to go down a little bit. I can also try to get the mic to you, but so if you already have a question, you can come here.
So you're using all these AVX 512 intrinsics, and then you mentioned you're on Mac, so you're not actually using them when developing locally. Does that mean you have two implementations of the same algorithm, or is there some way to use the same code?
Yeah, we have two implementations of all the algorithms.
Right. What if you also target like AVX2, but you don't have AVX 512? I think there's still a bunch of CPUs out in the wild that, like, do you have to write it 3 times, or are they?
Yeah, but we don't have to run in the wild. We just have a managed service, which is, yeah.
Thank you.
So actually I have multiple questions. So it seems like you jumped from using auto-vectorization directly to intrinsics. Is there any reason why you didn't go using generic SIMD structures and try to get that to optimize for the target platform automatically? Why did you go directly to the lowest, well, almost lowest level? You could have done assembly directly, but.
I mean, I think that the algorithm is so unique that I wouldn't rely on any sort of out-of-the-box SIMD optimization to leverage the full parallelism that you can. Like, a lot of the stuff we're doing is very strange. I mean, we could try it, right? But my gut instinct says that because we've actually factored every part of the algorithm around the intrinsics themselves, that it's worth going to the lowest level to get the highest performance.
Okay. Yeah, just wondering, because there might be some additional tricks that, you know, Rust does that you couldn't do. But then, of course, if you use very specialized intrinsics, then
yeah, I mean,
the Rust compiler might not be able to optimize that.
I think the performance, yeah, fair enough. It's worth a try.
So the other thing I was wondering about, you only talked about, you know, single-threaded implementations. What are you doing to get, you know, use of all the threads that are available in the course? Are you using Rayon, or is this really like?
Yeah, we use Rayon.
Okay. And a third question that I had is related to, you seem to compile the binary specifically for each architecture that you're running on. So you're not trying to compile for, let's say, different architectures at once and then do runtime decision on, you know, based on the features that are available, use the correct code.
Yeah, that's correct.
So you're compiling directly for the target and only for that target. And
yeah, we have like a Docker image for Ice Lake and Cascade Lake in our registry.
Thank you.
So I see 2. I'll first go here, then do.
Yes, thank you very much for your talk. The question I have is, like, at least in my experience, when like I'm going from AVX2 to AVX 512. It's not nearly even 2x performance. Usually you became very limited by memory bus.
Mm-hmm.
So I wonder, what is your experience? Like, did you experience the same problem? And maybe, like, do you have any plans to move to AVX 10 maybe, or any ideas about that?
I don't know about plans to move to AVX 10. I mean, I think the reason that we get such good performance here is because of the shuffle between registers, because we're not going to memory instead of, whereas in like the original implementation, maybe it is using AVX2 under the hood, but it's still going to memory. Here we get, I think, most of the performance gain from the register lookups, where we avoid the memory lookups.
Okay, thank you very much.
Yeah.
So I was just seeing the memory benchmark you did at the end there. I think maybe if you create a global allocator and just update the an atomic every time you allocate memory or deallocate memory, you can get a much more accurate view of how much memory your Rust program uses.
Good idea. Thank you.
Just add this, if you don't want Yeah, if you don't want to implement this, actually it's not very hard, but if you don't want to implement it, I think glibc and JA-malloc have some APIs to report the allocated memory. So you could, I think it's malinfo on glibc.
Yeah, I think we do use that in some places. Thank you.
So if you have any other questions, please come forward after we have a round of applause for Jack. Thank you.
Thank you.